Hi, I'm Meta Spencer. Now, this could be the most important show I've ever done. I think it's, I don't want to predict that it will be, but I'll tell you this, iron salt aerosols are the thing that I am pinning most of my big hopes on to save the world. This project is called Project Save the World, which is a bit ambitious, but I do interview people who have ideas about how to save the world from various global threats. And in my opinion, the worst global threat, the most imminent and catastrophic threat that the world faces right now would be the melting clathrates and methyl hydrates and permafrost in the Arctic. And so we've got to do something about that. And there are not many people who have any ideas about what to do. But I have two men here with me who think they know what may work. And that's what we're going to talk about today, iron salt aerosol. And in the University of Montpellier in southern France, we have Renaud de Richter. Hello, Renaud.
Hello.
Good to see
nice
you.
To meet you, Meta.
Ah, great. And in someplace in Switzerland, we have Oswald Peterson. Where are you, Oswald? Forgotten your city.
Hello, everybody. I'm in Kreuzlingen, which is near the German border in Switzerland.
Okay. He doesn't look like he's in Switzerland, does he? But both of you are heavily engaged in research on, and I guess a pilot project on the use of iron salts aerosol to remove, I guess methane, but maybe other things too, from the atmosphere. Since your face is already up here, Oswald, maybe you can start us off by telling the world what I can't begin to explain.
I'm very glad to introduce you into this new method. Our webpage is here. This is the webpage of AMR Earth, which is the company I have founded with Renaud and 20 other shareholders about 6 weeks ago, and it's called AMR, that stands for Atmospheric Methane Removal. And atmospheric methane removal is what we do, or what we want to do. We don't do it currently, but we plan to do it with this huge tower. Well, that's one means to do it, is to have a tower that blows iron salt aerosol that you mentioned, Meta, into the atmosphere. And we want to release it at 400 meters of height. That's why we need this huge tower. Of course, this is a photo montage, so it's not real. This doesn't really exist. That's a tower that somebody placed into this photo of that is actually St. Kitts in the Caribbean, but it will not be St. Kitts where we place it. Yes, it will be right next to the ocean, and there will be a ship right next to it, and all that is real, right? And there will also be windmills. So that is all sort of going to be true. But it's a vision. We don't really have the $25 million yet, which we need to build this. Mm-hmm. And this tower and this pipe, which runs within the tower, there is a small pipe running up that will inject iron salt aerosol into the atmosphere. And that's why we call it an atmospheric injection pipe. It's more like an ejection syringe for the atmosphere. And that is really what we want to do. We want the climate to get healthy with this syringe, right? So that's very similar to COVID in that we want to heal our planet with this atmospheric injection pipe. And the material that we put into is called ISA. That is short for iron salt aerosol. And that is a material that will act in the atmosphere to remove or to oxidize, more exactly, methane into CO2. This process, I think, is much better explained by Renaud.
Thank you, both. In fact, in the atmosphere, there are several natural ways by way the methane is removed. And one of them is the chlorine radicals, which are produced by the sea water and the sea salt, naturally by the UV light. And In fact, maybe 10, 15 years ago, it has been discovered that iron can catalyze. With very few amounts of iron, you can produce a huge amount of chlorine atoms, and you can accelerate and enhance this natural removal of methane by chlorine atoms. Right now, the
Chlorine.
chlorine, yeah,
Chlorine from salt.
sea salt,
Because,
from sodium chloride. And so it's not chlorine gas, it's chlorine atom, which is produced by the UV in a similar process that it's produced on the swimming pools. When you go to swim, there is a disinfection. In the atmosphere, the UV produces chlorine atoms, and they react very fast, 16 times faster with methane than the natural hydroxyl radicals, which is the detergent of the atmosphere, which removes all the other organic compounds in the atmosphere. It's a natural process also. And chlorine atoms react 16 times faster with methane than hydroxyl radical. And if you can catalyze...
You got now you're dealing with somebody who got a C in high school chemistry, and that's as far as I went. So I do understand NaCl. I believe that's salt. That's about my limit. So you're going to have to work real hard to help me understand what you're talking about. You're going to take iron salts chemically. What is this all about? And we're going to. What's going to happen? I mean,
can I help a little bit, because I'm very much the same as you, Meta.
Really? Okay.
I'm very, very bad in chemistry, so I always have to. Since I tried to run this project, I had to go to school and learn a bit more about this chemistry. But I have understood that it is a catalyzer. Now, a catalyzer is, and I do remember that from school, is something that is within a reaction, but does not really participate in the reaction. But it makes the reaction happen, but it gets out and it's still unchanged. It is not part of the reaction. So that was fascinating back in school when I was 17. And it's still fascinating because that's what we do. We do put something into the air and that makes a reaction happen, but itself, the ISA does not change. So it's a catalyzer.
Right? Okay, so the iron salt aerosol is mostly, it's a combination of iron and chlorine,
right?
That you get from doing, what do you put out there in the first place? It mixes with the chlorine in the air, in this salty air.
We will actually put out FeCl3, which is iron salt aerosol. That's Fe is
FeCl3.
3 atoms of Cl.
Okay, now that's going to do something to the salt in the air.
That is the salt. That is a salt.
That is okay.
It's iron salt. It's a salt of iron.
Okay.
So and that's it's a natural process. It already occurs naturally.
Yes.
When you have desert dust over the oceans with the wind, you have this sea salt from the sea breeze, and it reacts in the atmosphere, in the clouds, producing iron trichloride. And this iron trichloride, then it's the catalyst which will produce chlorine atoms, which will oxidize the methane. But then the sea salt regenerates the catalyst, provides again the chlorine which has been consumed. And the iron is not consumed.
What Renault calls iron trichloride, and I call FeCl3. And you call it ISA. That's all the same, right?
All right. Now, but the original source of this, I believe I saw in someplace that you get it in the atmosphere anyway from dust. That there's dust, and you said from storms in the Sahara, it blows across the Atlantic. Is that right? I'm jumping the gun, but I'm trying to understand where it comes from originally.
Well, any desert that has dust dust always contains iron, and therefore, if you blow dust up, then you always blow up iron. It's always in there. All the red, if you have red sand, for example, you know that in the east of the USA, everything is red, very red. Then it's iron. That is from iron. So, and in all sand, there's always iron, always.
Okay,
So,
you're just going to put more of it up there.
well, we will just enhance. That's why we call this the process. We call it EAMO. That is enhanced atmospheric methane oxidation. EAMO, because atmospheric methane oxidation is something that happens naturally. So AMO is already there. It's already, the nature already does it, and so we enhance that process. So that's why we call it enhanced atmospheric methane oxidation. Now, there's one word that is a bit difficult, and that is methane removal, because methane is not really removed, it's oxidized. So there is something that remains after the oxidation, and that is CO2. So we actually change methane into CO2. So it's not removed in that sense that people think about CO2 removal, where it's actually stored into the bottom of the earth or something. We do not remove methane. We oxidize it.
And we would not be normally thrilled with anybody who came along and said, I'm going to give you more CO2.
No, you wouldn't.
The only reason to be excited about it is it's so much better than the methane. that it's a good trade. Is that right?
That's correct.
In terms of greenhouse gas, you'd much rather have CO2 than methane. So if you can convert methane to CO2, we should all jump for joy. I understand that if you burn it, that's what happens too.
Exactly, right. So if you, for example, see a flare of a gas company, like if they burn off the methane, you see those huge flares from a chimney, then you think, oh, these are bad people. They are burning it in the air. Actually, these are not bad people. They're doing a good thing there, because if you burn the methane, and that's exactly what we want to do, then you get CO2, right? If you do not burn it, if you just leave out the methane without burning it, that would be much worse. That is because the methane in the atmosphere has a global warming potential, that's how we call it, 120 times higher than CO2. So the non-burned methane is the real problem, not the burned one. Because the burned one is CO2, and you're right, CO2 is also a huge problem. But one molecule of methane is much worse than one molecule of CO2.
The first thing that occurs to me is all those plumes of methane coming off the East Siberian Sea. And right. I saw a video of a ship going through that region, and it was like a plane flying through clouds. It was so thick with this white stuff coming up. And somebody said, well, don't smoke while you're there because it could ignite it. Well, if you could, why not just burn it then up there? And indeed, why are you going to use iron salt rather than just trying to burn it where you're going to do it?
Yeah, in fact, to be able to burn it, the concentration has to be about 5% at least. And in the atmosphere, it's only 0.002%. So it cannot burn. And very quickly, it's a very light gas who rises pretty rapidly and diffuses pretty rapidly. So it's very rapidly diluted. And so you cannot burn as soon as it's less than 1% or...
The idea is not so bad, because in some places there is actually burning methane in Siberia. And I've seen photos where you can see it actually burning, coming out of the ground and burning. And you're right, yes, that's a good idea. But you have to go to many places to burn it.
But your real plan is not to do it in the Arctic, no. But in over the ocean someplace. And that's because that's where there's salty air. Is that right?
There's two reasons why we want to do it near the equator. and on the ocean. The first reason is to drive this process, you need energy. And energy in this case comes from the sun. So this whole process, what I said, like where Isaac actually makes methane oxidize into CO2, needs energy. And the energy is solar energy, that is UV light. Now, in the Arctic, you have very little UV light because the sun is not shining. Actually, half the year there's no sun at all. And then in the other part of the year, it's very stormy, bad weather. So the UV light is very bad. Whereas at the equator, the heat is much, so you need as much sun as possible. That's why I'm here in this wonderful Pacific island, because here the sun is shining, right? So that's one big thing. We want lots of sun. In the night, it doesn't work. It only works at daytime. It only works when the sun is shining. So, for example, if there is a huge hurricane, then it works much less because then there's much less light. Okay, that's one reason. And the other reason is that when it comes down, we would prefer to fall into the ocean rather than on land. But that is not so important. It can also fall on land. It's not dangerous or anything.
Okay, now you've just punctured my biggest hope, because what I was hoping is that you guys would go up to the Siberian Sea and set up your pipe and spew the aerosol into the atmosphere and handle it there, because that's where it's really concentrated. You know, this methane coming out of the bottom of the ocean is the scary part, or at least the most risky, immediate, urgent problem. But it sounds like your plan won't work up there. We have to do it in the, really, oh dear.
You can't do it there because there's too little sun. Right? It would work, but it wouldn't work as well as on the Pacific. And if you go up to the height where we want to operate, it's 400, 600 meters, somewhere there, then the concentration, even near a methane source in Siberia, is not so very different from the Pacific. The concentration is always around 2 ppm, that's part per million, or maybe sometimes 3 ppm, but it doesn't really vary very much in this height. Of course, at the bottom, near a source, yes, it would be much stronger. But then you could again go back and say, avoid the methane in the first place, because when you are at the source, you can just say, all right, let's stop the source, so it's not coming out at all. And that is what we recommend for sources, right? We want, of course, we recommend that methane sources are stopped.
Yeah.
But that's another approach. We want to take that methane out of the atmosphere that cannot be stopped. And that is right.
So that's already all around the world, about evenly distributed?
Yeah, it goes 10% up or down. It's very evenly distributed. So it doesn't really matter where you are. It's very even. Yeah, I think if you go, for example, to the Permian Basin, where you have lots of oil leaks and gas leaks from the oil industry, then it would be maybe 4 ppm, so a bit more, but in that height, right? And you want to do it at a great height, because then it will stay in the air for a long time, right? If you don't do it at big height, it will just drop into the ocean and then it's gone. Mm-hmm. And it's quite expensive, this stuff. Yes.
Why not have airplanes fly along and spew it out? Because they go high anyway, and they're going to be up there.
They're too high. We want to be between 500 and 1,000 meters, but airplanes are at 11,000 meters, so they're way too high. Therefore, we can't use airplanes. Yeah, we did think about airplanes. Yeah, that's your thoughts are very good. We went through all of them, but we ended up where we are now, where we say we have to build this tower and bring it up into the air at that height, exactly that height. It could also be a bit higher. It could be 600 meters, but of course, it would cost a bit more.
Okay, now what happens? You go up there, you spray this stuff,
right?
And it goes. What kind of diameter of a region would this thing cover? One tower, for example.
Compare again to nature, right? If you look at nature, look at the Sahara, where it blows up. Most of it comes from Mali, as I understand, and it is blown up and it goes over to the Amazon. and it fertilizes the Amazon.
Yeah, that's amazing. Yeah.
5,000 miles away, right? So,
Uh-huh.
and we want to do the same. We want it to travel for thousands and thousands of miles. And we want, the best would be if it never came down, but it will come down, right?
Okay.
But, yeah, the best would be for it to stay up there for 10 weeks or 8 weeks. That's my hope, really. But we cannot really prove how long it will stay up there until we have built it. So we hope that it will stay up there as long as possible. There are many parameters, and again, Renault would be in a better position to explain, but in principle, you'd say the smaller the particle is, the longer it will stay up, right? Because then it's clear. We have learned so much now through COVID about particles, right? About aerosols. Everybody knows like 2 years ago, nobody knew what an aerosol is. Now everybody does. And the COVID aerosol stays in above the ground. If I sneeze it, I'm almost 2 meters, I'm 190. So if I sneeze it out, then it can stay above ground 16 hours, right?
Oh, really?
So that's how long it can infect somebody, right? So if we get the same, if we get it like 8 hours per meter, then you have 400 meters times 8 hours. That's something
Now,
like,
okay, now you got this iron stuff in the atmosphere way up, but it stays there and it is a catalyst that makes other things happen.
right.
And it stays there and continues doing it again and again.
That's
And
correct.
what is it that Renault, you've got to explain this one to me. What is it that it is affecting and turning into what up there? And what happens to it? Does this stuff fall out? The CO2 spray around? What's the residue after the iron aerosol has done its job? What do you have left over and where does it go?
The first step is the iron trichloride, the catalyst. With the UV light, will generate a chlorine atom, which will remove hydrogen from the methane. And then you produce hydrochloric acid, but this already occurs in nature. And you will produce radical methyl, which will react very fast with the oxygen in the air, very rapidly through reaching the oxidation state of carbon dioxide. And the HCl, the hydrochloric acid, will be recycled in the clouds, in the humidity, and with the sodium chloride from the sea salt, it will regenerate the catalyst, iron trichloride, which will start again generating a chlorine atom and reacting again with methane. And this stays in the interface between the water vapor and the gas phase, the oxygen and the nitrogen in the atmosphere, and you have this transfer from one phase to the other phase, which occurs naturally very fast. I hope it was relatively clear.
Okay, so is there any reason to be worried about whatever's left over? You talk about hydrochloric acid. Well, I mean, that's is that a problem? I mean, do we have to worry about having too much hydrochloric acid in our world after you guys have finished your task?
In fact, currently there are around 300 ppb per parts per billion of hydrochloric acid along all the coasts, and much more along the coasts which have a lot of pollution. And it naturally occurs that when you use your car, you produce some nitrogen oxides, which are pollutants in cities, which give ozone, etc. And these nitrogen oxides will produce acidity in the atmosphere, and it reacts naturally with the sea salt, and you will obtain sodium nitrate, and they will release hydrochloric acid. So when you take your car and near the coast, you are already producing acidity with the carbon dioxide, and with the nitrogen oxides, which react with sea salt and release already hydrochloric acid. So the concentration of 300 or 350 parts per billion of HCl is already natural and there along all the coast. And also when the ships or when the power plants burn fuel containing sulfur, they will release SO2, sulfur dioxide, which will be sulfur dioxide, SO2.
SO2?
Dioxide.
This is like bunker oil exhaling.
Yeah. So in fact, the sulfur pollution, it's very well known from all the power plants and the ships who burn fuel, heavy fuel, bunker fuel that contains sulfur, and they release this. They burn it, and so it releases an oxide of sulfur, and in the atmosphere with the oxygen, this produces sulfates and hydrosulfuric acid, and this one will react also with sodium chloride from the salt and release hydrochloric acid, HCl, and the sea salt will be transformed from NaCl to Na2SO4, which is a sodium sulfate.
Is that a problem? That's
sodium
a problem.
sulfate? No, that's not a problem. It's already occurring everywhere because of the human pollution.
Yeah, but it's not good.
No, it's
already.
Not,
I mean, it's not something we are celebrating, right?
No, sure.
No.
But this also occurs with the volcanoes, which release a lot of large amounts of hydrochloric acid and hydrosulfuric acid. And there are many different natural emissions of acidity in the atmosphere. And this one, it will not produce much more acidity that already exists. And this is recycled in the process to regenerate the catalyst, iron trichloride, and generate the chlorine atom that will destroy the methane, that will oxidize the methane.
We don't want to put any more acidity into the ocean, but isn't what you're going to do going to put more acidity into the ocean?
Not really, because the acidity will come from the ocean. The chlorine comes from the sea salt, which already comes from the ocean. And in fact, all the carbon dioxide we breathe and we emit with our cars and our trucks is an acid. So we are just using this acidity. And the process uses it, but we're not producing more.
Oh, okay. Well, I feel better now. Okay. So now you're going to clean up the whole world. You're not going to specialize in the Arctic. Well, I have to find somebody else to help me with the Arctic, but because I think we got to worry about that first. But you're going to put up these towers, and how many of them do you need? Here comes a friend of mine named Paul Beckwith, and Paul is also a climatologist. Hello, Paul.
Hello,
nice
Paul.
To see you.
Paul.
In Montpellier.
Great to meet you, Paul.
I couldn't come on at the beginning of the call.
Okay, I was just asking them. They've got me worried now because they can't fix the Arctic as quick as I want them to, because they have to specialize in parts of the ocean where they get sunshine, and there's not enough sunshine in the Arctic. So it looks like we've got to work on some other approach, Paul, if we're going to solve the Arctic. But
well, you can do it on, you can cool the ocean currents that go up northwards towards the Arctic, like the Gulf Stream as it crosses the Atlantic, right? For example, you know, and moves northward. You can target certain areas, you know, where lots of heat is transported up to the Arctic.
Maybe, do you want to do another quick recap of what we've learned, what I hope I have learned so far, and then Paul can pick up from there and ask and introduce comments. I was about to say I want to know what kind of an operation it would be to try to actually remove the methane from the atmosphere sufficiently, but by the technique that they're proposing, how many of these towers they need and where they put them and things like that. So, oh, here comes Oswald's little diagram again. Oswald or somebody, start over and back up a little bit and recap our conversation.
That's right. With Paul, I will start with the EMO, that is enhanced atmospheric methane oxidation. That's what we plan to do. So atmospheric methane oxidation without the enhanced is something that occurs in nature. That is a process where methane oxidizes. So that's CH4, and it oxidizes and turns into CO2 and water. So that's a normal process, and all methane actually does that. And then the methane is gone. So that's the normal oxidation. Now, if we say enhanced, means that we will put a catalyst, which is called ISA, or iron salt aerosol, into the atmosphere, or we plan to do that. And that we will do at 400 to 600 meters of height. So that's why we need a huge tower to bring it up there. And then that will act as a catalyst to make that atmospheric methane oxidation happen more frequently. So then the lifetime of the methane will be shorter, right? Now, at this stage, lifetime of methane is about 12.4 years, has been calculated by very good scientists, and we just take over that number, and we want to shorten the life of methane to half. So that would be 6.2 years. Now that would halve the content of methane in the atmosphere, and that would bring the methane content in the atmosphere back to pre-industrial level, because pre-industrial level is about 0.7 parts per million, and now we are at 1.9 parts per million. So it has not only doubled, but 2.5 times more methane is in the atmosphere now than it was, let's say, naturally. Let's say before industrial age, it was natural, right? That's the natural methane content, and we want to go back to that methane content that nature had. We don't want to destroy all methane because it is not the natural methane content to be at zero, even though there is nothing that methane does. Like if you would reduce all CO2 out of the atmosphere, then we would all die because the plants couldn't live anymore, right? So the CO2 is really important. Whereas methane, theoretically, you could take it all out and nobody would die, right? So, but we don't want to do that. We want to only reduce it to the normal, to the natural level it had before industrial times. Okay, which means we have to halve its lifetime. And to do that, we want to create this enhanced atmospheric methane oxidation process. Okay, is that good enough for you to jump in, or do you have any questions, Paul? Or
yeah, one question is that 12.4 years is a sort of globally averaged lifetime number. You know, the OH radical concentration is quite varied with latitude, I think. So wouldn't the methane lifetime in the Arctic, for example, be much longer than the lifetime at lower latitudes? Of course, there is mixing and global circulation, but if you have sources of methane in the Arctic, then the concentrations there are, you know, of course, much higher. And part of that is because there's much less water vapor up in the high Arctic, and there'll be much less hydroxide radicals as a result. So have you looked at that variant sort of? So I mean, where would you locate these towers on the planet?
We would locate them near the equator because we want as much sunlight as possible. The sunlight will drive the process, and we need UV light. And that is one reason. And the other reason is we want to be near the ocean, because favorably we would want the ice to fall into the ocean rather than on land. And again, we would like to be on a Pacific island because the Pacific has less iron than the Atlantic. And therefore, the iron would be more beneficial to the ocean in the Pacific than in the Atlantic. But that is, again, not so important for us. The most important process is the atmospheric methane oxidation. And we do not go to the Arctic, even though you're right, their concentration would be a bit higher. But at the height where we are, at 400 to 600 meters, that difference is not so big. And therefore, it is more important to have the UV light, right, for the process to happen. And therefore, we will go near the equator. That's our plan. At this stage, this is all a vision, a plan. It's not tomorrow. Mm-hmm.
Right. Have you thought, like the big advantage of this method is that, you know, the sort of the foreseen negative consequences are really minimized because, you know, it's just iron. It's like it's you know, salts, right? It's not it's quite different from putting sulfur up into the stratosphere, for example, in terms of the possible you know, negative effects. But have you thought about how have you thought much about getting sort of public acceptance of this idea? I mean, it's kind of crazy, but you probably are aware of the SPICE project, where they wanted to put water vapor into the atmosphere from balloons, high altitude balloons.
Right.
And that project was stopped or halted recently because, you know, just because of public perception.
That's
right.
True.
And I mean, I just made a trip through Northern Ontario, and I went through industrial towns like Sudbury, where they actually built we had the acid rain problem in North America. So in a lot of the source was in Sudbury, the nickel mining. There's a lot of sulfur released in the smelting, and it was destroying all the vegetation locally in the town and turning Sudbury into kind of like a moonscape. So they put in the super stack, they call it. It's actually a 380 meter tall smokestack. They just did stuff like that. Like there was no public outcry saying you can't do that. And, you know, we live in a world where, you know, companies can build huge industrial infrastructure and strip away the boreal forests and tear down into the soil 50, 100 meters with huge scrapers to expose the bitumen. I'm talking about the tar sands or Canada's oil sands. And then, right, we're doing, meanwhile, some scientists want to put up a balloon, you know, high and release some water vapor and maybe some calcium, and there's public outcries and they get shut down. So we're in a crazy world right now. If they didn't say anything and just did it, right?
How do we
deal with that? Like, how do we, I mean, it's almost like we need a billionaire to fund this project.
Yeah.
And just go and do it. So like, have you looked at maybe, you know, Elon Musk or this?
Yes. Of course, finance is one problem we have, but finance is not the biggest problem we have. The biggest problem is, as you say, is public perception. And public perception in our day and age is something that goes very fast. I mean, you can sort of build something for 3 or 4 years, and then suddenly you get a shitstorm in Facebook, and then it just goes down in 2 days, you know, and then it's gone. So you have to be very, very careful about your public image.
You know what I think it is? There's just one word, and it triggers everybody's fears. It's the word geoengineering. If they hear that word, game over. You can't do it, whatever it is.
I think we have.
You know, I mean, geoengineering could conceivably cover everything, including planting trees, you know.
Yeah, I mean, just don't use that word. The thing about these storms, though, I mean, you're right. You could do a project for 3-4 years, nothing, goes on Facebook and gets the social media virus, and then there's a storm. What the thing is, the trick is you just ignore the storm.
I think there actually is some kind of international law saying you can't do something without permission anymore.
No, that's not. That is not really the problem. I think Paul is quite right that the public image is really, really something we have to be very careful about. But then again, you see, we have to acknowledge that geoengineering is just a word. And the word, we shouldn't be frightened by a word.
Yeah.
And what we want to do is we want to manage the global climate. So call it global climate management. That's a better word. We have to do this. There's no other choice. We have to realize that man has to come to a point where we have to manage our climate like we manage everything else. We will have to manage our climate. And don't call it geoengineering, call it global climate management. And
or global climate restoration is what, there's a group called the Healthy Climate Alliance.
That's right.
This is Peter Firekowski. Yeah, it's climate restoration, right? Is the idea to bring CO2 down to pre-industrial. So this is to bring methane down to pre-industrial. Have you considered getting some sort of smaller, more modular device that could go on, you know, at mining sites? When they mine, there's often natural gas released from the oil, and then they have a choice. They can either flare it off, burn it from the smokestack and flare it off, or they just release it. Or, you know, there's a methane leak from time to time, like the one in California that went months. So is there a device that you could envision that could go on, that could, more portable, that can go to a really strong source of methane? Like, so the choice is flaring it or releasing it to the atmosphere, or perhaps your device could neutralize the methane from a point source.
I am working on this type of devices to address local sources of concentrated methane before it gets diluted and before it gets the atmosphere. One of them is by photocatalysis, and the other one is by generation of chlorine atoms, but not releasing it in the global atmosphere, containing them in the ventilation system. And in the States, there are more than 100,000 abandoned oil, gas, or oil wells. I mean, gas wells.
Leaking methane.
Abandoned coal mines, underground coal mines. And many of them are leaking methane. And so we're also working, not with Oswald, but we're also working on this type of addressing the local sources of concentrated methane.
Right, because I think you know, the best way presently is to flare the stuff, right?
Yes.
I mean that's better for the environment than just letting it go up in raw form.
When it's possible, yes. It's not always possible.
Sometimes you can actually use it because methane is quite valuable. So
yes, but usually the problem is getting, you know, it's hard to transport. It's not like the liquid. It's not oil. Like oil is very easy because it's a liquid. It's a perfect, you know, perfect substance to fuel industry, right? Because it's, you know, it's like it's a lot easier to transport than coal, even, for example.
It's warm here in this room because there's methane, and it's a good thing. Methane is not a bad thing.
Yes, exactly. I mean, it's just natural gas. Yeah. So
methane is it's the same with CO2. I mean, now the CO2 bashing that is going on, it's that stupid, because CO2 is what plants live on. This is very essential, and it's a very good thing to have CO2. It's just a little bit too much. It's always
exactly. A lot of, I mean, ISA marketed as sort of like a scrubber for methane.
That's right.
I mean, what really reduced the acid rain problem was the scrubbers on like electrostatic scrubbers on smokestacks.
Yeah, that's perfect. That was good. That was really good. But now we have to be aware of the fact that this pollution also had some beneficial aspects, which we have also cleaned up, you know. And I don't want to go back to pollution. I don't say, oh, we have to go back and get rid of the scrubbers, but we have to manage the climate. We have to go to a point where we actually decide how much of this and how much of that is in the atmosphere. And of course,
can I go back to where I was about to ask a while when Paul came in, and that is, how many of these towers or installations are you going to need to reduce the atmospheric methane by how much? How big a project would this have to be? I understand, I believe that you say you're working on a pilot project now. What's the status of the thing you're doing? You're the manager, so what are you managing and what do you hope to manage?
Well, we have 3 phases of our project, and the first phase is now, and we have founded the company, and we have a very small amount. It's just friends and families. And Renault, but he's also friend and family. We have 100,000 francs, which is not very much, and then we do a lot of research with that. Now, the second phase will be to build a preliminary project where the tower will be 36 meters, and we will then sort of build a 1 to 10, so 10 times smaller tower with a small sprayer, and then we will test the whole technology. And that will be, it's not all decided, probably built in Europe, and then it will be transported to the Pacific Island, and then it will be rebuilt there, and then we can test it on site, right? And then when this testing is done, so that will take, say, 1.5 years altogether, and we need about $1 million for that, not 25, but $1 million. Then if that is all fine and we can say it works, we can prove it does actually reduce the methane and we need so much to reduce so much methane and so on, then we will hopefully get the 25 million, which we need to build the big tower, right? And of course, we don't really have 25 million in our pockets, so we need to find somebody who will help us with the finance. But then again, as I said before, I don't think that finance will be such a big problem because it's a very, very attractive idea and we will find the finance. But the public image is what we have to care for. That is really the risk. And Paul is really, he's found the right spot. If we are not careful with the public image of this, it will die. We will, in the end, need about 20 of these towers. So if it's all done, we will have 20 of these towers near the equator on all different islands.
Okay, now let's say this would remove something like half of the methane in the atmosphere because you want to leave the other half there for good reasons. But now that just takes care of methane, but you still have CO2 and nitrous oxide and chlorofluorocarbons and other greenhouse gases, right?
That's right.
So how much of an impact would these 20 some odd towers do out of the total greenhouse gas problem, the whole global warming problem?
It would not solve the problem, but it would contribute to the solving of the problem. And I would say it would stop the warming. If we tomorrow could put up those 20 towers, which we can't, but if we could start them tomorrow and blow the stuff out, then we could, I would say, stop the growth of global temperatures for about 10 or 20 years. After 10 or 20 years, then it would not work anymore because then the CO2 growth would kick in and then it would again start growing. But we could stop it for some time, maybe 10 or 20 years, the growth of temperatures. And that is very valuable because what we need is time. We still have to revert all our economy and go away from CO2. There is no way away from that. We can't replace that. And we are not We are very much in favor of all alternative energies, of all electric cars, all that has to happen, but we just don't have enough time. And this will buy us time. It will buy us maybe 20 years. And then stop doing it again, because then we won't need it anymore. Right?
Well, I think the next step in the discourse about it is people will say, well, what harm will it do? And if you can say what are the worst things that might be the result of what you're planning, what are the potential bad side effects that one must take into account as objections to doing it?
Well, there's cost. There's cost. It costs a lot of money.
That's not enough. What people will want to say is, they will talk about putting sulfur in the atmosphere, and then somebody will talk about things like, well, all the things that could happen from sulfur. But the environmental impact of this, are there any potential negative side effects?
Well, I think that's maybe a better way to look at it is it's really a methane scrubber device. So it removes pollution. In fact, you don't even need to mention climate change with this device. You can just say that the methane levels from industry are too high, and this device is exactly like this is an anti-pollution control device. And then talk about the history of the industrial processes that put, for example, sulfur dioxide and particulate matter up into the atmosphere. So then what they did is they put new technologies on the smokestacks to remove the sulfur, to not let it go into the air at all. These electrostatic scrubbers, pollution scrubbers, right? But they can't get rid of the methane. So now we just want to do the same thing for the methane. We want to scrub the methane pollution out of the atmosphere. Sure, the side effect will be that it will reduce climate change significantly. But if it was marketed as a geoengineering thing, then yeah, it'll be halted. So it's very easy to market it as doing something else, and then the side effect is to.
All I'm saying, Paul, is before they ever put that big smokestack up, somebody should have said, yeah, but look what's happening. If you do that, it's just going to go someplace else.
Right, but that's not how people work.
The argument should have taken place immediately before they even put the thing up.
Of course, but but things don't operate in a logical fashion like this. I mean, we build nuclear bombs and then we figure out how to regulate them.
Nowadays, people will say, well, tell me first what might go wrong. Tell me the bad news or what might happen.
It doesn't work, and then methane goes way, way up. It's very hard to make a case that reducing methane is something can go wrong. If it either works or it doesn't work. It removes methane or it doesn't.
For example, I asked, are you going to add hydrochloric acid to the ocean and make it more acid? And then I was assured, no, that you're just putting back what you got. You're not making it more acid. So that handle that argument. But there may be other arguments. Oswald, I'm sorry. Yes.
Can I help you a little bit with that? Because there's at least a group that says that it might be risky to have it in the ocean, and you have already hinted at that point. So there's really no big resistance against the part that is called atmospheric methane oxidation. But the stuff eventually will fall into the ocean, and then it also does something, And there is some people, we don't say that, we think, and we are very convinced actually that it is beneficial for the ocean. But there are other people who say that it is not beneficial for the ocean because it fertilizes and it does and can create a bloom of algae. So then you have more plants growing, and there is people who say that this is not a good idea. We say actually because it's diluted so much and we will spread it over thousands and thousands of square miles before it reaches the ocean. The concentration will be so little that it will be something like 0.1 milligram per square meter. So like nothing at all. And therefore it is actually beneficial. We do say that, but they to help you because there's other people who will attack us and they will attack us with this argument. They will say, you are doing ocean iron fertilization, and that is not good. And then they will come with a big geoengineering.
Okay, so then all you need to do is you need to compare the levels of iron that go in and the dispersal to iron that goes into the ocean from the dust from the Sahara Desert.
Exactly right.
Right, and you could show that the concentrations are minimal compared to dust blowing in. So you could argue, well, if this is harmful, then you have to stop the Sahara Desert wind from blowing the dust into the ocean, right? Which has been going on forever.
That's right. Yes, and
right.
also,
So you compare it to natural processes, right? And also you emphasize that this is, this is to restore the conditions to what we had before.
And the technique also mimics natural things. It's a nature-based method. And in fact, the nature has been doing this aerosols
yes.
For millions of years. And in fact, one thing that could be wrong would be to go back to glacial period. If we could
if you do too much of it, yes. And the other thing is, it would seem to me that there should be a huge interest with the natural gas industry for funding this research.
We are reaching out to them, but we are still very small. We are in the infancy of our project.
Right, I understand, but I mean any of the companies that are extracting natural gas and transporting it. Of course, I mean, the industry's been exploding. Natural gas was touted as a bridge fuel, and it turns out that, of course, with, that was just that was just propaganda. It's a bridge fuel. I mean, the leak, with leak rates of approaching, 5 to 10% leak rates, it's worse than coal, natural gas.
That's true.
Okay, I hope that you guys will be, if you haven't already, try to get contact with John Kerry, because he's the guy with the power on this issue, and you ought to make sure he knows what you're doing. Okay.
Yes.
Okay. Yes. One last word. What is it you want to say, Oswald, before we wind up?
I want to repeat what Barack Obama said. I just want to say, yes, we can.
All right. Great. Beautiful. Thank you all. This has been fascinating, and I will be watching for further developments for sure. Keep me posted. All right.
Thank you.
Thank you.
Thanks a lot.
Okay. Nice meeting you.
Nice to meet you, Paul.
Okay. I should read all of your literature and documents and stuff, and then we should have a technical call about.
Did you see our?
I'm very interested with what you're doing. So it's great stuff. It's great.
Good.
Thanks a lot, Paul. Go through our website. Yeah.